The first step in taking graphs and treating them as topological spaces was to realize them geometrically. Remember, we had this idea of the geometric realization of the graph, which took us from a finite combinatorial object and turned it into this subset of Rn that we could treat as a topological space, which allowed us to do wonderful things like define drawings and embeddings of graphs and define things like planar graphs and reason clearly about things like crossing numbers in graphs. So all those topological ideas for graphs started with this geometric realization. And now that we've taken this time to think about generalizations of graphs, that is, simplicial complexes, in higher dimensions, we can apply the same kind of definition to simplicial complexes to get realizations, geometric realizations of simplicial complexes. So that's what we're going to do today. So remember, we had this geom. I have a long pause here. I want to call it a functor. It is in fact a functor, but you could just think of it as a transformation that takes us from a graph to a topological space. And today we're going to kind of, well, it's not just going to be a graph, but a simplicial complex to a topological space. And the definition is going to be very, very similar to the one we used for graphs. So the first step is to generalize line segments. Recall that the edges in the geometric realization of a graph were embedded in Euclidean space as line segments. So if we just remember the definition of a line segment, if A and B are 2 points in Rn, we can write this line segment as the set of all points that looks like this. I'm going to do 1 minus t times A plus t times b. Now I'm doing scalar multiplication and addition because I'm treating these points as vectors in Rn. Okay, and that's for all t in the range from 0 to 1. This is how you parameterize a line segment. Okay, so that's key here. This is the one parameter version. Alternatively, we could use 2 parameters, and that might actually be more natural as we get into higher dimensions. So I'm going to call the convex closure of a set AB is going to just be the line segment AB, but I'm going to write it as follows. It's the set of all points, which are of the form T0A plus T1B. So right off the bat, you see that there are 2 different parameters here, a T0 and a T1. And the properties that they have to satisfy are as follows. T0 plus T1 have to equal 1. They have to add up to 1, which if you viewed T0 as 1 minus t and T1 as t, then you would see that that's equivalent. And the second condition is that they have to be non-negative. So T0 and T1 are both greater than or equal to 0. And that condition is covered by the requirement that t is in 0, 1. So these 2 definitions of the line segment are equivalent. They're just different ways of expressing the same set. But what's useful now about having more parameters is that when we have sets that are more than just 2 elements, we can extend this definition in a straightforward way. In this case, the convex closure of a whole set of points, so in this case sigma is a set of points in some Euclidean space, is going to be the sum of ti vi, where the vi's are the points in sigma. And the sum of these parameters ti should be 1, add up to 1, and they're always greater than or equal to 0. I didn't put it in here, but this is, again, for all I, ti is greater than or equal to 0. So I have a non-negative linear combination where the coefficients add up to 1. Whenever you have a sum of vectors that have all been multiplied by a scalar, that's a linear combination. If all of the coefficients are non-negative, that's a non-negative combination. If the coefficients add up to 1, that's an affine combination. And if it's linear, non-negative, and affine, it's a convex combination. So that's how we define the convex closure set of points. Now, this seems perhaps way more abstract than just a simple line segment, but it's not too hard to see that if you took 3 points like this and you took their convex closure, you would get the triangle. This is all convex combinations of those 3 points. So the convex closure of the 3 points is the triangle, and so the triangle generalizes the line segment in the same way we had 3 points sets and sets with larger numbers of points to generalize the edges when we went from graphs to simplicial complexes. So hopefully you can see that there's a clear geometric relationship between the sets of points and the shape that is their geometric realization. Okay, so now if we have a full-on simplicial complex K, and let's number our vertices. And for a particular vertex, we're going to do the same thing we did for vertices in graphs. That is, we're going to just embed it as the standard basis vector in Rn. So ith standard basis vector. It's all zeros except for the ith coordinate, which is a 1. And for a simplex, it's going to be the convex closure of its vertices. So in other words, it's the convex closure of this set of points, geom v for v in sigma. And as with the graph, the geometric realization of the entire complex will just be the union of all these things. And this is a little cleaner for the simplicial complex because unlike the case of graphs where we had to explicitly write down the union over the vertices and then the union over the edges, since the vertices are just simplices of cardinality 1 or dimension 0, they're already in here. So I could just sum over all the simplices in K of their geometric realization and just take the union of all these. Sorry, I said sum, but you know I meant union. All right. So this will give us from a simplicial complex, which again is just a combinatorial object, especially as we're going to limit ourselves to finite simplicial complexes. So it's a finite set of vertices and a subset of its power set that's closed under taking subsets. I now get this subset of Rn, which is the geometric realization of the simplicial complex. So this is kind of the standard way to go from a simplicial complex to a topological space. And I should mention at least one little caveat. Given that I wrote this, I should tell you that we'll define the geometric realization of the empty simplex to be the empty set. So it doesn't contribute to this union, just for completeness. So we're going to prove a fact which is going to help us to get our head around the definitions. And this is going to be relatively simple to prove, but I think it's a good one to look at for two reasons. One is that it gets us right to the heart of the definitions. And in terms of what this geometric realization looks like as a set of points in Rn, but also because this is the fundamental property which in fact becomes the definition of a certain kind of geometric simplicial complex that gets used extensively in many areas of computing. So this simple property about the intersections of geometric realizations is really important. So here's how it works. It's saying that if I take two simplices, sigma and tau, in a simplicial complex K, so they're both simplices in K, then the intersection of their geometric realization is equal to the geometric realization of their intersection. Another way to say this is that if I take the two simplices and embed them, their intersection is a subsimplex of both of them. That is, they intersect at some common subsimplex. So this is maybe the way this is phrased colloquially. Simplices intersect at a common subsimplex. But of course, when you say this, we are talking about simplices after embedding them in Euclidean space. So let's prove it. If I take any point, I can always write it out using coordinates. So I could think of it as a big long vector of n coordinates, or if you like, I'll write it in terms, actually I can tell you what these are. Let me say what they are. This is x0 all the way up to x n minus 1. Sorry, it's very tiny, but you know what I mean. And I could also just write this as the sum of the xi's times the standard basis vectors. And this is the unique way to write it in terms of the standard basis vectors. That's kind of what it means to be a basis, is that there's a unique set of coefficients where you can write the point as the sum of the basis vectors times those coefficients. So that's some point in Rn, and if in particular, if it's in simplex sigma, if it's in a geometric realization of a simplex sigma, then it can be written as follows. So I'm going to write it like this. I'm going to say that x is in geom sigma if and only if x equals sum alpha I bi for vi in sigma. Now, I wrote alpha I here because by definition it just says there has to be some set of coefficients, but we know what the coefficients are. We actually know that they're xi. And similarly, I could write the same thing for tau. And so in fact what it means is that the coefficient xi is going to be non-zero if and only if vi is in sigma. And again, as the same thing holds for tau, it means that vi also has to be in tau. If it's in both, it's in the intersection. So the coefficients in this point are going to be non-zero only for the coordinates corresponding to the vertices in the intersection. So it implies that we could take this summation here, which was for all I in n, and we could limit it to just the i's corresponding to vertices in the intersection. So x is actually equal to this sum of xi bi for all I such that vi is in sigma. I'll write it like this. Now, we know that this is all of the coefficients, and we knew that the sum of the alpha i's was equal to 1, and therefore the sum of the xi's is equal to 1. So this is a convex combination, and so this is true if and only if x is in the, let's write this as the geometric realization of sigma intersect tau. And now, just to recap, that means we have a point, it's in the intersection of both sigma and tau, if and only if it's in the intersection of sigma intersect tau. All right, let's use this, this geometric realization to get back to something we saw again for graphs, which was this idea of a linear drawing. We said that a drawing was going to be a continuous map. Usually we did drawings in the plane or in R3, but it's some linear map from Rn to some other Euclidean space. I'm sorry, a drawing didn't have to be linear, but a linear drawing is a particular kind of drawing. And one useful thing about having linear drawings is that you can reason about them geometrically. But another useful fact is that we know that linear maps from Rn to Rd, right, where n and d finite dimensional vector spaces, these are always continuous. So we can kind of skip a lot of the work of proving that our functions are continuous, because we know linear maps are continuous, and therefore the restriction of a linear map to just the geometric realization is also continuous. Okay, so we're going to let f be the restriction of our linear map to this geometric realization of a simplicial complex K. Now, if f is injective, then, well, injective drawings are embeddings, so this would be an embedding. And since f came from this linear map, this is actually a linear embedding. So this would be a linear embedding if it's injective. If it's not injective, it would just be a linear drawing. And it has all the properties you might hope. It's going to keep flat things flat. So just as with linear embeddings of graphs, where every vertex ends up as a straight line segment, in the geometric realization, it started as a straight line segment, but it will continue to be a straight line segment with the application of a linear map. And now the same thing will hold for other simplices. A triangle will stay flat, a tetrahedron will stay flat. And hopefully as you play with this a little bit, and you'll have a more elaborate, let's say, should I say complicated? A higher dimensional notion of what flatness actually means. All right. So one thing to point out here now is a simplicial complex with a linear embedding in RD is sometimes called a geometric simplicial complex. And you might even see in the research literature people talking about abstract simplicial complexes, which are the complexes we've talked about so far. And they're just distinguished from geometric simplicial complexes because now it has topology, it has shape. And so here, for example, this is a simplicial complex with 1, 2, 3, 4, 5, 6 vertices. Its geometric realization lived in R6. So there was a linear map from R6 to R2, and if we restricted it to that complex, we get a nice embedding. And this embedding, assuming my lines here are straight, these are my, I won't say my best effort, but my effort to make them straight, and the triangles living in the plane are also flat, and so this gives us a linear embedding from a complex which lived naturally, its geometric realization lived naturally in R6 into the plane R2. Okay, so this is a geometric simplicial complex. And you can already start to see, hopefully, why this kind of object is useful. Perhaps the most common way they get used in science is this idea of piecewise linear interpolation. Really should be called piecewise affine interpolation, but it is what it is. So you've seen this before. For instance, in high school, I'll bet at some point you looked at functions on the real line. So f here is a function, say, from R to R, and I've drawn its graph. And if I only know the value of f at some fixed set of points, I can interpolate for points between the known points. For example, in this case, I've got the point x, and it lives on a line between a and b. So I could write x as some linear combination of a and b, that is, it's going to be alpha times a plus beta times b. And in this case, I've done it in a careful way so that alpha and beta are greater than or equal to 0, and alpha plus beta is equal to 1. Right? It's a convex combination of a and b, and these are the coefficients of that convex combination. If you want a real concrete example, imagine I happen to be right midway between a and b, then alpha and beta would each be 1/2. But for any alpha and beta that have this property, I get a point on the line segment between a and b, and if I know the value of the function at a and b, so I know f of a and I know f of b, I can do this interpolation, which fills in the gap between them. So I put a little hat over f here. This is my approximation. And the approximation is quite simple. I'm just going to take alpha times f of a plus beta times f of b, where these are the same alpha and beta as up here. And the effect of that, if you think of this graph, remember the height of the curve is exactly the function value. I wrote it in here for b, so you see that the height here is f of b. In the approximation, that's like lifting x up to this point that's on the line segment, the straight line segment between a, f of a, and b, f of b. So it gives me a piecewise linear interpolation, and so this hat version of the function is the one that goes straight line, right through. Okay, this is a very useful way to extend a function from a finite set of values to the whole line. And it's especially useful in computer science where if you're computing something and you want to store a function and it's not easily expressible, say, as a polynomial, it doesn't have some short representation, you just know the values at some set of points. Well, if you only want to store that finite set of values, you could then extend it to the entire line in this case, or at least some subset of the line that you care about. Right, so this is used a lot. Now, the same idea can be used as well in higher dimensions, but once you get beyond the line, you have to make some choices. In particular, you have to make some choices about how you break up the plane. On the line, once you pick a set of points, it naturally breaks it into a series of line segments. But if I have points in the plane, I might have to choose how I divide the plane up into, say, in this case, triangles. There's vertices, edges, and triangles. So if I have an embedding of a simplicial complex, in this case, since I'm embedding it in the plane, it has to be at most a two-dimensional simplicial complex. So the largest simplex has 3 vertices. But I have that embedding. Now I can look at points in the image of that embedding, and I can use them to interpolate a function. So, for example, in this case, I have a, b, and c. That's the image. This is where I've embedded these 3 vertices. So x is equal to some convex combination of a, b, and c. Let's call it alpha a plus beta b plus gamma c. It's a convex combination, so it's non-negative. So alpha, beta, and gamma are all greater than or equal to 0. And it's affine, so alpha plus beta plus gamma is equal to 1. And the interpolation is just what you would hope. It's going to be alpha times f of a plus beta times f of b plus gamma times f of c. So we just took the same combination of the function values to get the function value at x. And this is like, if we imagine now the graph of this function as living in 3D, right? It's some kind of surface. This is sometimes called a terrain, because I've got the points and their function values, gives us a point in 2D plus its function value gives us a point in 3D. Well, if I took those 3 points, A, B, and C, lifted up here in 3D, and I take the triangle that they span in 3D, x gets lifted directly up onto that triangle. That's how linear interpolation works. And again, this allows us, if we have the complex or the triangulation of the plane, we can take function values at the vertices and extend them to the rest of the space. All right, so more generally, if I have any simplicial complex and any function on the vertices, I can do a linear extension or a linear interpolation of that function onto the rest of the complex. So I just take any point x, again, in the geometric realization, and I'm going to define this interpolation to be the following. It's the sum over all indices in n of xi times the function value at vi. Okay, so again, vi is in vk. These are the vertices of vk. And it's worth noting that often, just as when we proved our little fact before, these xi's, let's say many xi's are going to be 0. Especially if the simplices are not very high dimensional. So in the case we saw with the plane, where the largest simplex had 3 vertices, then every point in the geometric realization has at most 3 non-zero coefficients. Right, that follows straight from the definition. So, but we can still write it as a sum over all the vertices, just where many of the coefficients are 0, because we saw that already. The coordinates are 0, and so the function values of those points don't contribute to the overall interpolation. Okay. All right, so there was a bunch of stuff in there, a bunch of different topics about relating the geometric realization of a graph to the geometric realization of a simplicial complex. Then we talked about what a particular kind of embeddings of geometric realizations of simplicial complexes. I would love it if there were words that had fewer syllables than geometric realization and simplicial complex. But anyway, we took linear embeddings, and those were, of course, directly related as well to the kind of linear embeddings we saw of graphs. But then we looked and saw also how the coordinates of the geometric realization could be used for function interpolation. And so this is kind of the first hint at where these simplicial complexes creep into many areas of science, in particular for solving systems of, or solving partial differential equations, where at every step you have some function on a space that you want to approximate, and so you do it by interpolating the function values on the vertices. Often that's done linearly. So we will start to get back down into graphs with the next video, but for now I think it's been hopefully fun to see how the same or at least very similar notions for graphs get pulled up into higher dimensional generalizations in simplicial complexes. So see you next time.